Good day, everyone. Before I start my presentation, let me introduce myself first. My name is Amira binti Amer from University Malaysia Sabah. Today I will share my research with you all, and the title of my presentation is Compressive Strength of Interlocking Compressed Earth Brick Units. Okay, let's start. This is the outline of my presentation today, and it consists of 9 parts, which are: the first and second part concern about the background and literature review of my research. The third and fourth part will discuss about the type of material used and how the samples were produced and prepared for the testing. The fifth part will show the method, and I will explain the procedures of the testing on the next part. Then I will talk about the measurement. Last but not least, I will present the results and discussion before proceed to the conclusion. Well, let's move on to the first part, introduction. Interlocking compressed earth brick ICEB is one of the alternative methods for industrial building system that has been developed to comply with the Green Building Construction Standard. It is intended to replace the conventional fire-clay brick methods. The main materials are soil stabilizers such as cement or lime, river sands, and water. Instead of using firing method, the ICEB is produced by using manual compaction machine or high-pressure hydraulic compaction machine. The method of construction is dry stack, which also known as mortarless brick. The ICEB units usually comes with tongue and groove features as shown in figure 1. Next, the wall automatically align vertically and horizontally through the dowels installation. Okay, the next slide is the compressive strength of the ICEB units. According to Shaizul et al. 2020, the compressive strength of the ICEB influenced by the degree of compaction and age of the samples, while according to Patankar et al. 2018, materials, method of manufacture, and rate of loading is the factors that determine the compressive strength of the ICEB units. Well, there are no standards to determine the compressive strength of the ICEB units. Therefore, most researchers refer this standard to determine the strength. Henry et al. 2014 in the book of Design of Masonry Structures state that the minimum average compressive strength of the load-bearing brick is 5 Newton per millimeter square, which comply with the minimum requirements specified in BSEN 1998 and BS 3921. However, according to Malaysian Standard 76 1972, the minimum compressive strength for load-bearing brick is 5.2 Newton per millimeter square. Study by Zakaria C. Muda et al. 2013 and Muhammad 2016 shows that the compressive strength of mortar filling is higher than ICEB without mortar fill. This shows the mortar filling increases the compressive strength of the ICEB units. Moving on to the next slide, research by Saari et al. 2017 and Nasri et al. 2020, steel plates were used to create a flat surface prior to testing, and the compressive strength found out to be exceeding the minimum requirement for compressive strength. The compressive strength test usually tested in dry and wet condition, where the wet condition indicates the worst case scenario with the lowest compressive strength value. This is due to the liquefaction of unstabilized clay minerals and the formation of poor water pressure in the brick matrix, as well as the loss of strength during the immersion process. Next, I will talk about the material used to produce the ICEB units. In this study, the soil used consists of 8% fines and classified as well-graded sand with clay SWSC by Unified Soil Classification System. The sand used was river sand and water was free from any impurities. Ordinary Portland cement having property as shown in Table 1 and Table 2 were used as a binder in the study. Next part, samples. The sample used was standard ICEB unit with dimension as mentioned here, and this is the picture. The sampling method according to BSEN 771, where the minimum number of sample for each test is 6. Next, method of testing. The ICB unit was tested using BSEN 772-1 standard under two different methods with 5 different conditions as shown here. The first method required the tongue to be removed and the sample be tested under two conditions, which were condition 1 without mortar fill and condition 2 with mortar fill as shown in figure 2. While the second method was kept both sides of each samples with steel plates to ensure that the two bed surfaces had a flat surface for compression in three different conditions, which were condition 3 is a dry condition, condition 4 is wet condition, and condition 5 is oven dry condition. The ICEB units were dried for 24 hours after production and cured twice a day for 7 days. The curing later was reduced to twice a week for up to 28 days curing. The procedures for testing also referred to BSEN 772-1, where the air dry conditions were tested according to the procedures in which the sample were oven dried at 105 degrees Celsius for at least 24 hours and cooled at room temperature for at least 4 hours before testing. The wet condition sample were tested by immersing the sample in water at temperature of 20 degrees Celsius for 24 hours and drained for 20 minutes before testing, while the oven dry condition requires the sample to be dried in the oven at 105 degrees Celsius until constant mass is reached at 24 hours interval. The samples were then tested by universal testing machine with loading rate of 4 MPa per second. The compressive strength measured by dividing the maximum load achieved by its net loaded area. For condition 1, the net loaded area calculated based on the smaller net loaded area of the two frog bedface, while the rest of the conditions are based on the basis of the gross area of the ICEB unit itself. Now let's see the results and discussion of this study. The first one is the effect of mortar filling on the compressive strength. As we can see from the figure 4, there is only slight difference between the compressive strength of ICEB unit tested without mortar filling and with mortar filling. Although there is an increasing value in compressive strength due to mortar filling, the percentages is pretty low, where 1% increase at 7 days and 0.6% increase in strength on 28 days. Next, the effect of testing method katang versus steel plate. Condition 3, which using steel plate gave highest compressive strength for both sample edge compared to condition 1, where tongue has been removed. This might due to physical damage and cracking caused by grinding procedure to remove the tongue. Last but not least, the effect of moisture content on ICEB compressive strength. Figure 6 shows oven dry has the highest compressive strength for both edge, followed by air dry and wet condition. Wet condition has lowest compressive strength, which is comparable to the research carried out by Abdullah et al. 2010, which stated that as moisture content increased, the compressive strength decreased. This is due to the formation of pore water pressure, and water caused the binder to soften. As for the conclusion, this study shows that ICEB units which are kept before testing on both bed surface gives higher value compared to cutting the tongue of the samples to provide parallel plans prior to testing. Second, the compressive strength of ICEB units with tongue removal and mortar filling is 1% and 0.6% higher than that of tongue removal and without mortar filling at 7 days and 28 days respectively. The ICEB units can therefore be tested without mortar filling as indicated in BSEN 772-1 as the net loading area of the sample with frogs is more than 35%. Third, the compressive strength of ICEB in oven dry condition is higher than in a dry and wet ICEB condition. Finally, the fourth one, ICEB units may be used as load-bearing masonry walls as their lowest compressive strength under all conditions, with the exception of wet condition, is 5.11 Newton per millimeter square, which is above the minimum requirement of 5 Newton per millimeter square. That's all from me. Thank you for watching.